in this first approximation. The splitting is unimportant. So this entire model is based on equilibrium. Okay, so this is the kind of metallic state that it's saying. But what is important to see is that all these pictures tell you that as soon as I put in the slightest amount of holes, the system will become metallic. That's the reason I didn't talk about doping holes in the metal. That will make the metal metal. That's no big deal. But if you take an insulator and any amount of hole you put, immediately it will become metal. So let's go back to this and ask the question that what really happens. So actually these compounds can be made. And I have taken only the ones that are insulating to start with. LaTiO3, remember, small gap insulator, BO3, all these are insulators. I have put strontium, doping holes. All of them should become metallic. This one becomes metal, this becomes metal. This does not become metal for any amount of doping. This has becomes a material which is metallic at some temperature, insulating at some temperature. This, you can go on putting as much strontium as you want, up to 50% strontium, and it will not become metal. This becomes readily metal. Which means this simple explanation that I pointed out completely fails in explaining why. In fact, even the extent of X required to make it metallic seem to depend on the material you are using. While the pictorial representation says that even 0.00000001 X should make it metallic, it turns out that you need X in the order of 5%, 10%, 15%, 20% in these cases to make them metallic. At lower percentage they are insulating, and at higher percentage the metal. This and this never becomes metal, and this gets into a state for some values of X such that it is metal at some temperature, insulating at some temperature. Which means there are things that we don't understand.
Cold doping slightest cold doping will make them metal. Similarly, slightest electron doping
also will make them metal.
The other thing.
Absolutely. Then the Fermi will move up there and move up there. You are absolutely right. Most of the reason I talked about hole doping because that's where most of the games are. But people have talked about electron doping. The neodymium cuprid that I was talking about there, the electron doping was the game that people are playing. But in general, most of the time it's lanthanum doped with strontium that people look at. But there are other cases, strontium doped with lanthanum, like in double perovskite, SF2Fe06, people have tried to do that. So those are things. You're absolutely. I'll not explain why this happens. There is something that we are trying to understand. There is no clear understanding as of now. But this is where something that Sushanta was mentioning, disorder plays a very important role. And that is the essential. Which means the periodicity. That is the underlying theme of every concept that you have developed breaks down. Because a periodic model can never explain the existence of an insulating state in presence of arbitrary amount of doping. Okay. But then these are caveats that I want you to appreciate before I move on. Okay, now let us get to, now that the electronic structure is defined by U, Coulomb interaction strength, delta, the charge transfer energy, T, the hopping strength. Tomorrow I'll be dealing with how we use the experiment to estimate these quantities. Today I'll show you how theoretically we can estimate these quantities, or we have. I've forgotten what time did I start? Or what time?
15 minutes, 45.
Under 15 minutes? Yeah. So let me go on with it. Okay. So for a given compound, let's try to estimate that. How do we do that? Let's start with T. The T, remember the hopping strength, which was the idea, the concept that we introduced in the tight binding model. So we'll go back to the tight binding model and try to understand. So essentially the idea of what we are going to do is, let me tell you in a very simple terms, the hopping, I'll set up a tight binding model which I have to first decide what is the model. That means the range of hopping, remember, that I talked about, nearest neighbor, next nearest neighbor, next to next nearest neighbor. And also which are the orbitals that I'm going to include, because I can have AS, P, D, many orbital and oxygen also, or some other compound, whatever their partner element. So I need to define which are the orbitals that I think are at least required and what is the range of interactions that are required. So the way from theory we try to extract is that first I try to do as serious a calculation as I can do, which is not tight binding, which is as ab initio as I can, as rigorous as I can, including as many orbitals as possible because that's the most accurate. And I get the band dispersions out of those calculations. Band dispersion is to get E versus K plot for that. Then I take a tight binding Hamiltonian, a model Hamiltonian, based on which are the orbitals that I think are relevant and which are the hopping that are relevant. Then I ask what value of hopping gives me the result from this tight binding Hamiltonian, which is very similar to the really serious calculation. When this mapping is done properly, then I know those are the values of the tight binding Hamiltonian parameter that are good. So let me illustrate that. And I'm going to illustrate that with a 2,6 semiconductor, zinc sulfide, I'll take, going away from oxide. This is exactly the Hamiltonian that actually Shushanka wrote in the morning in a different way. This A dagger A, he had written it as, if you remember, plus minus the operator. He had written it that way. And remember? So basically, or also it could be this. This annihilated a minus state and converted it into a plus state, which is exactly here, that this state gets annihilated and this state gets generated. And he had a J, which I have made as T, my hopping state of T. This is the Hermitian conjugate of that. And he also had these states, which are, right? This is the convention that you were using. So he had a two orbital basis.
Point that the expectation value of each of these projection orbitals is actually the probability of occupation, and these are precisely the A dagger A kind of terms which are number orbitals.
Absolutely. And that is exactly what you're seeing here. And this is also seen, and this is the diagonal energies. So this is equivalent to the orbital energy that I talked about. Remember epsilon S, epsilon D, epsilon. So these are the diagonal energies. These are the hopping strength. These are the ones that I am after. This we call the on-site energy or orbital energy. This is the hopping integral. So I want to find out in zinc sulfide what is the minimalistic tight binding model that gives me good result, and goodness being defined by it being similar to honest to goodness best calculation that I can do. And so the minimal model, zinc sulfide, so I should have sulfur P states because that's the highest occupied level. And I should have at least zinc S state, but I know zinc S and P are degenerate nearly. So maybe S and P states both I would require. So the minimalistic level that I would say that let's have sp3 states in both zinc and sulfur. So I'll take at the zinc side S and 3p orbitals, and also at the sulfur side I'll take S and 3p orbitals. And I'll take the nearest neighbor hopping only, zinc and sulfur. This is the honest to goodness calculation of the energy versus momentum. Momentum is written in along some symmetry directions. These letters denote some momentum value from here to there, etc. Like gamma corresponds to k equal to 0, 0, 0. Other points I don't remember what the values are, but essentially it is a momentum axis.
This is based on exact numerical calculus for the Hamiltonian that you've given for some finite system?
No. This is an infinite calculation. It's a DFT calculation, which we believe. Now, I don't want to get into the all the controversy of why DFT works, but in DFT, because we can experimentally determine the band structure, it turns out that DFT calculations match exactly those. So, honest to goodness, DFT calculation with all orbitals or many orbitals in the basis in a plane wave. This is an LN2 variety, but you can do a very rigorous today LATW with many plane wave bases and do a calculation on the basis.
But do people also do, like, I set up the tight binding model on a real space and do a numerical diagonalization of some finite system?
That is precisely the motivation why we did all this. In fact, we are the ones who first did that for the finite calculations. No, because basically the reason was that we were making zinc sulfide nanoparticles and we wanted to get a transferable set of parameters. So our attempt was to start with parameters that simulate the bulk correctly and then use that in real space calculation such that, and we needed to do tight binding, otherwise the kind of number of atoms we were trying to handle would be impossible to do. I've been sure, 10,000 atoms. In tight binding you can do that, but otherwise it would be impossible. Because otherwise you have to evaluate those integrals, which is key. Okay, so sorry for the detour. This is the band dispersion, which is the truth in this particular definition. And this is the, by varying those epsilons and t's, the best that I can do. Okay? Within that tight binding Hamiltonian. And if you'd see that these states don't exist here at all. But that is not a problem because these are actually these are coming from zinc D states. Zinc D state I have not included. So obviously it will not come here. But that's the reason, let's say, we ignore that zinc D state. And let me pull this one and put it on top of that. You can see that I'm not getting this part right. Black, the truth goes that way. Red is very bad. This part also very bad. So many parts, though with sp3, overall some of the descriptions are right, but some of the parts are very bad. Which means that I have not been able to get the thing yet right. And we are interested in the band gap of the material and how the band gap would change its size and things of that sort. And the band gap is defined here. These are lowest energy. These are all occupied states here. These are all unoccupied states. And the band gap, the lowest energy gap, is here. And that part is not getting simulated correctly, which means we are doing very bad. Let's get the band gap part right. So that means that the model that you have defined was not good enough. Then we tried to understand where the model is going wrong, and we found that the zinc D states actually contribute quite a bit towards the top of this blue line. Is density of states contribution. The black is the density of states, and the blue is the contribution from zinc D states into the top of the valence band. Likewise, sulfur D states contribute quite a bit to the bottom of the conduction band, which is this one. Which told us that sp3 is not a good basis, we must bring in the D states also. So we bring in the sp and D states. So now it becomes even bigger. And then we calculate how it looks like. And it turns out that best sp3 D5 fitting is here. Now you see the D states in the tight binding coming up because I have included the D level. And you can see that now you see it has improved. But there are still some places where things are not good. For example, here, there we have this big dip, it is very flat. Here it opens up this much, but here it's nearly degenerate in the same place. Here it is flat, here I get a dip. So some of the details are still not good. So what am I missing? Then by analyzing it further, we realize that what we are missing is that, I'll not go into the detail how we do that, that's in the next transparency, that essentially says that sulfur-sulfur interaction is also very important. Because so far we were only doing the nearest number zinc to sulfur and sulfur to zinc hopping. But it said that sulfur to sulfur hopping is also very important. So then we expand further our model and say that it is that sp3d5, zinc and sulfur, I add in sulfur-sulfur interaction also. And now you see that this becomes nearly degenerate, like over here, which was very big gap. Then this part comes out right, it's no more flat. This part begins to get a dip, not as much, but quite good. So essentially, and this is the density of states from the truth, this is the density of states from this tight binding model. So now we have got the model that you are happy with. So that is the way we build up the tight binding model. And now the one that has given this good a fit and this good a fit tells me what the hopping strengths are. So the T's get defined by fitting the tight binding Hamiltonian model that I define to what I consider to be the truth. Okay? That's how T is extracted. Here is an example, and you find it very difficult. LAMNO3, this is the truth and this is the tight binding model. And you can see that they look almost identical. So that I now know from this model all the manganese D oxygen P hopping. This was created with a tight binding model that only had manganese D and oxygen P and oxygen P and oxygen P interactions. So all the hopping interactions are defined. So T is known. How do I determine U and delta? U is what I'll cover quickly. It's a very interesting concept that was introduced by Herbst and Watson in the 70s, and that brings out the screening concept that I've referred to in my earlier talk. Remember, this Coulomb interaction is what I'm after. Now, that essentially is the energy difference by taking one electron out from one place and putting it at another place, right? So, essentially, the energy that I'm talking about is an energy associated with taking an n electron system, making it n minus 1, and simultaneously taking another n electron system, making it n plus 1. You understand that? Because here, this was an n electron system, I make it n minus 1. At the same time, an n electron system, I make it n plus 1. And the energy associated with that process is exactly U, as was shown over here. The energy difference between these two is U. So this is the energy that you are interested in. So that is, they had called it delta minus, that they call it delta plus, essentially to add an electron to one side and to take out an electron. This is the ionization energy, this is the affinity energy. So the energy difference between the ionization energy and the affinity energy added together is the Coulomb interaction energy. That's the electron removal, that is the ionization energy, that's the lower Hubbard band. This is the electron addition energy in chemistry, and that's the upper Hubbard band. And the energy difference of the two added together is the Coulomb interaction strength. But we are talking about metals and not atoms. So when I move one electron from one side to the other, all the other n electrons that I talked about, I pretended that they don't respond, but they respond hugely. Simply because a metal cannot allow a potential gradient inside itself. The free electron will respond to screen out that potential. And so the other electrons respond hugely, and how do they respond? So what they have said that every charge fluctuation will be compensated by an opposite fluctuation in another orbital on the same site, which means a complete screening. If a d electron fluctuates, an s electron fluctuates the other way. If you increase the d electron by 1, s electron will pump out itself out of the site, making the number of electrons the same at the same site.
Sorry, on terminology, by charge fluctuation, you mean the same thing as valence fluctuation which we used to.
It is exactly the same. Right?
Like in samarium sulfide.
Samarium sulfide, we were talking about F7, F6. So one electron was being removed in and out. And that is connected by U. But here the point is that as soon as in a metal, if you put an electron in a d level, localized on one metal, the s electron of the metal will move out from there, keeping the number of electrons more or less the same, to screen this additional Coulomb strength. So they say